Hi, this is a lesson on geometric optics, which is also called ray optics. And this lesson is divided into 3 parts, and this part deals with the concepts of reflection and refraction. All the pictures that you see in this video are attributed to OpenStax College Physics, which is a book distributed under the Creative Commons Attribution License by openstax.org. Geometric optics, or ray optics, is about studying how light behaves when it interacts with lenses and mirrors. And to do this, we draw diagrams and figures which represent light using rays, which are essentially, on a page, just lines, straight lines, with arrows showing the direction of propagation. So this would be a ray representing light that's propagating to the right. So this picture is showing a ray of light interacting with the surface of a flat mirror. There's an incident ray, which is the light shining toward the mirror, and the reflected ray, which represents what the light is doing after it reflects off the surface. And so this figure is showing one of the fundamental laws of ray optics, which is called the law of reflection. And this law defines the relationship between what's referred to as the angle of incidence, which in this picture is labeled theta sub I, and the angle of reflection, which in this picture is labeled theta sub R. And the law of reflection says that those two angles, theta I and theta R, are equal to one another. So the interesting thing here is to notice how these angles are defined. These angles are defined relative to this dashed line that goes down the middle here. And this dashed line is referred to as a normal line. And the reason is because in math, normal means perpendicular, and that dashed line is perpendicular to the surface where the ray of light strikes the mirror. So here, to summarize one more time, the law of reflection says the angle of incidence, theta I, relative to the normal line, is equal to the angle of reflection. Here's a demonstration of the law of reflection. What I have here is a beam of light which is directed toward a flat or plane mirrored surface. And you can see that the normal line is labeled on this apparatus. And the incident ray coming in from the right is striking the surface of the mirror at an angle of 30 degrees relative to the normal. And the reflected ray, which is going down toward the bottom of the screen, is reflected away at an angle of 30 degrees relative to the normal. So the law of reflection is verified by this simple experiment. Light reflects off of rough surfaces as well. And in situations like this, the law of reflection is still obeyed. But now, in this picture where you see this rough surface and these parallel rays of light which are striking the surface, it's just that everywhere where these rays strike, the surface has a differently oriented normal line represented by these black lines. So in each case, for each ray pictured in this figure, the ray is obeying the law of reflection, but because the surface is irregular and not flat, the reflected rays are diffuse. They diffuse in all directions. This is the type of reflection that happens off of most surfaces in the real world, including a white piece of paper and you. Have you ever looked at a fish in a fish tank or a straw in a glass of water at a restaurant and noticed a strange optical effect? What you're observing is the consequences of a different law of ray optics or geometric optics called the law of refraction. This phenomenon of refraction occurs because when light travels from one medium to another, so for example, in the case of the fish tank, when the light travels from the water through the glass into the air, its speed changes. The speed of light in a vacuum, like the vacuum of space, is 3 times 10 to the 8th meters per second. That's 300 million meters per second. The speed of light in air is about the same. Air does not change the speed of light very much. However, the speed of light in water, as it's propagating through water, is somewhat less. It's only 2.25 times 10 to the 8th meters per second. So when it comes to refraction, we can, it turns out that the ratio between the speed of light in whatever medium you're studying, whether it be water, glass, or air, relative to the speed of light in a vacuum is a very important parameter for understanding how refraction occurs. This so-called index of refraction is defined as the speed of light in a vacuum, c, divided by the speed of light in whatever material you're studying. So for water, the index of refraction for water would be the ratio of 3 times 10 to the 8th divided by 2.25 times 10 to the 8th, which is approximately 1.33. The speed of light in a material such as glass is even less, about 2 times 10 to the 8th meters per second. So the index of refraction of glass is greater than the index of refraction of water, 1.5 versus 1.33. So the rule is, the greater the index of refraction, the slower light travels, the smaller the speed of light in the medium to which that index of refraction belongs. So why would a ray of light bend when it passes from one material into another simply because the speed of light in those two materials are different? That's exactly what's happening when you observe refraction. So this figure is trying to show an analogy of a lawnmower that is traveling from one material, one ground surface to another. Here we have a ray of light which strikes the interface between two materials with different indices of refraction. And it bends when it encounters this interface. The angle at which the ray of light comes into the material, labeled theta 1 here, is called the angle of incidence. The angle of the refracted ray relative to the normal line is called the angle of refraction. So here we say the angle of refraction is less than the angle of incidence. All right, well, let's take a look at what the lawnmower is doing. Why? Let's consider when the lawnmower travels or passes from the sidewalk into the grass is rougher than the sidewalk, so the lawnmower slows down. But the lawnmower doesn't strike the grass all at one time. This wheel right here strikes the grass first. And because it strikes the grass first, it slows down first because it's trying to travel across the rough grass. So because this wheel slows down, it causes the entire lawnmower to pivot until all the wheels are in the grass, and the net effect is the lawnmower has changed direction. So light behaves in a similar way. Light travels through space as wave fronts, and different points along that wave front strike the interface between the two materials in question at different times. The part that strikes first slows down first, and this introduces a kink in the wave front. And the net effect after the wave passes completely from one material into the other is the wavefront has changed direction. The ray of light has changed direction. So in general, when you have a situation like this, where you're going from a material where light travels fast, which is the sidewalk in this analogy, into a material where light travels more slowly, which is the grass in this analogy, the index of refraction of the grass is greater than the index of refraction of the sidewalk. And this causes the ray of light to change direction. The angle of incidence relative to the normal is going to be larger than the angle of refraction. The ray of light, in other words, the ray of light has bent toward the normal. It emerges from the boundary, traveling closer to the normal line that passes through the boundary, which is the dashed line in this picture. All right, now in panel B, we see the other scenario where the lawnmower or the ray of light travels from a material where it travels more slowly into a material where it travels more quickly. The lawnmower goes from grass to sidewalk. The ray of light goes from a large index of refraction into a smaller index of refraction. And what happens now is the light ray speeds up, and this causes it to bend away from the normal. So in this scenario, the angle of incidence is, or the angle of refraction, which is theta 1 in this case, is greater than the angle of incidence, which is theta 2 in this case. All right. So you got to be careful with subscripts. The angle of incident in this picture is labeled theta 2. The angle of refraction is labeled theta 1. The situation is reversed over here in panel A. So to summarize, if a ray of light travels from one material into another and the ray slows down because the material into which it's traveling has a greater index of refraction, then the ray of light is going to bend toward the normal, like in panel A here. On the other hand, if the ray of light travels from one material into another that has a smaller index of refraction relative to where it's coming from, it'll bend away from the normal because it speeds up. It would be nice if we had a way to quantify the relationship between the angle of incidence, the angle of refraction, and the indices of refraction of the two materials on either side of the boundary. And we do. It's called Snell's law. If we consider a situation like what's pictured here in panel A, where theta 1 is the notation for the angle of incidence and theta 2 is the notation for the angle of refraction, then Snell's law is this. The index of refraction of the first material, n1, times the sine of the angle of incidence, theta 1, equals the index of refraction of the second material, n2, times sine of the angle of refraction, theta 2. n1 sine theta 1 equals n2 sine theta 2. So we can use this equation to make predictions about what a light ray will do when it travels from one material into another if we know the angle of incidence and we know the indices of refractions of the two materials. Let's take a look at the law of refraction in practice here. So what I have here is a ray of light that's coming in from the right-hand side of the screen, and it's striking an acrylic lens. And probably can't see, but the angle of incidence relative to the normal line at this flat boundary, this planar boundary between the air through which the light is propagating and the acrylic into which it travels is 30 degrees. The angle of incidence is 30 degrees. And when the ray of light strikes the acrylic, it changes direction and it emerges from the acrylic lens at 20 degrees relative to the normal line. So the angle of incidence is 30 degrees. The angle of refraction is 20 degrees. The light ray has bent toward the normal. It's got closer to the normal line. Why? Because the index of refraction of acrylic is greater than the index of refraction of air. The ray of light has slowed down. It's changed direction. It turns out that whenever a ray of light strikes an interface between two materials that have different indices of refraction, even if the materials are completely transparent, a small amount of the light actually gets reflected and obeys the law of reflection, like what's pictured up here. You have an incident ray striking the boundary between material with index of refraction n1 and material with index of refraction n2. Part of the light gets reflected and part of the light gets refracted. So the situation that's pictured on this figure here is a situation where n2 is less than n1. And in this situation, the light is going to speed up when it exits n1 and enters n2. And this means the ray of light is going to bend away from the normal. And another way of saying that is theta 2, the index or the angle of refraction, is greater than theta 1, the angle of incidence. So if you make the angle of incidence sufficiently large, eventually you'll reach a point like what's pictured right here in panel B, where the angle of refraction is 90 degrees. And when you reach this so-called critical angle, which is labeled theta sub c in this figure here, none of the light actually emerges from the boundary. None of the light exits from N1. Instead, all of the light gets reflected from the boundary. So even if you're dealing with two completely transparent materials, the angle of incidence can be sufficiently large in a situation like this, where the light is speeding up when it exits, that none of the light exits at all. You get total internal, what's called total internal reflection. All of the light gets reflected. So let me demonstrate this, total internal reflection. So here, entering from the right-hand side is a ray of light that passes through a piece of acrylic and strikes a boundary between the acrylic and air on the other side and exits out the left-hand side of the screen here. And you notice the angle of incidence is about 20 degrees, and the angle of refraction is about 30 degrees, reflecting the fact that the light speeds up when it goes from the acrylic into the air. Now watch what happens. Oop. See if I can do this. Let me pause. So I've increased the angle of incidence here. Now the angle of incidence is about 40 degrees, and the angle of refraction is 70 degrees. Increase the angle of incidence a little bit more. Now it's about 42 degrees. And now the angle of refraction is getting very close to 90 degrees. In fact, very little light actually emerges from the other side of the lens. But notice a significant amount of the light gets reflected back the other way. If I increase the angle of incidence even more to approximately 50 degrees here, now all of the light is reflected. None of the light emerges from the lens. This is called total internal reflection. The angle of incidence is sufficiently large, it's beyond the critical angle, so that the angle of refraction is mathematically, in Snell's law, greater than 90 degrees, which in the real world is impossible. You have reflection instead of refraction. So this phenomenon is very useful. So total internal reflection is this phenomenon, to summarize, where the index of refraction of the material into which the ray is traveling is less than the index of refraction for the material where the ray comes from. And in situations like this, so the ray of light is going to speed up when it goes from N1 to N2. And it's going to bend away from the normal. So the angle of refraction is going to be greater than the angle of incidence. And in situations, again, where the angle of incidence is greater than some critical angle, which in this figure is denoted theta sub c, you're going to see total internal reflection. None of the light will emerge from the boundary. Instead, all of the light will be reflected back into the material. So Snell's law, N1 sine theta 1 equals N2 sine theta 2, can be used to determine what this critical angle is. The critical angle, mathematically, the critical angle is the angle where the angle of refraction, theta 2, is equal to 90 degrees. So when theta 2 equals 90 degrees, theta 1 is equal to the critical angle. And the sine of 90 degrees is equal to 1. So Snell's law becomes N1 sine theta sub c equals N2. or the sine of this critical angle, is equal to the ratio of the indices of refraction, n2 over n1. Solving for the critical angle theta c by taking the inverse sine, the arc sine of both sides, the critical angle is equal to the inverse sine of n2 over n1. So this just about ends our first lesson on ray optics, dealing with the properties of reflection and refraction. But one more topic. Let's talk about the phenomenon called dispersion. And so what's pictured here is a ray of light, a white light, that's passing through a triangular prism. And the ray of light is going to be refracted at both boundaries between the prism and the air as it passes through. And if you've ever done this in real life, what you'll see emerge from the other side is not white light, but a rainbow of colors. Something happened so that the white light was separated into its constituent parts: red, orange, yellow, green, blue, indigo, and violet. So what's happening here is that it turns out that the index of refraction is a little bit dependent on the wavelength of light. The index, for example, the index of refraction of red is smaller than the index of refraction for violet. So when red light, which is part of the white light that's incident on this prism, strikes the boundary between the air and the prism on this side, it bends a little bit less than the violet light. And this creates a separation. And the separation is made even more dramatic when the light exits the far side of the glass prism. And the colors that were all combined as white light, when they entered the prism, have become dispersed, spread out, separated when they exited the other side of the prism. And you see a rainbow. So this phenomenon is occurring when you see a rainbow during or immediately after a rain shower, except instead of triangular glass prisms, you have spherical water prisms, raindrops, that are creating this, that are causing this phenomenon. So this concludes the first part of this three-part lesson on ray optics, or geometric optics. In the next lesson, we'll talk about image formation using lenses.